All right. So because the beginning of this lecture is really a continuation of what we're discussing on Monday. Let me start by reviewing a little bit what we were talking about. So I'm just scrolling up. This is my lecture notes for Monday. So what we saw, we considered quite generically congruences of geodesics and on all geodesics, because for us that's more important. I mentioned that there's something similar for timeline geometrics. There's something not as similar, but there are also studies of a congruence of curves that are not particularly geodesics. And we saw that there is a particular equation governing in which the curvature appears that governs how the acceleration of vectors that indicate that the separation between the multiple geodesics in the family, how they evolve along the affine parameter. So that provides with an interpretation for the curvature tensor to begin with. And then we saw how we solve so what the equations for Z, supposing that it commutes with the tangent vectors. And then we had the nz's, because it's a first order differential equation. So we had an nz's. So we were able to write as a matrix, so Z evaluated in a generic point in the affine parameter. We saw that it was ambiguous and all that, but it's a matrix. It is a function of V times the initial value at a certain point Q. And then we wrote a decomposition of the gradient of V into certain quantities. I did mention the interpretation very briefly, but I missed a brilliant opportunity when we plugged this form of nz's into the equations. I missed the brilliant opportunity of commenting the geometric meaning of this equation, and you can see. So let me do it now. I mean, I was all the time referring to the fact that these determinant, this theta had to do something with the areas, or the tangent of these cross sections of these congruences. But now it's explicit when you write in this form, because remember what this E is. E is the transformation of a vector between the 2 points. And the determinant, as you remember for what probably either linear algebra or multivariable calculus, so the determinant of the transformation, it measures precisely the area, so or the volume or hypervolume. So this theta is saying precisely the relative variation of the area, because this is two-dimensional, because because these are null geodesics. So this is just the derivative of the logarithm of the area, or 1 over the area, the derivative of the area itself. So I think if there was, I mean, you could already interpret the meaning of these quantities, the vorticity, shear, and expansion, from the definitions. But if there was any doubt, I think this formula clears out. So I forgot to mention this. And then we saw a nice condition. Well, then we derived the equation for evolution that came from the second order derivative, from the second derivative. And we saw that it's particularly interesting to look at the trace of this equation, and that led to the Reichel-Durius equation, which I wrote here. We saw that there are in certain circumstances, this vorticity to be 0, one of which is when you're looking for conjugate points, and you know that E is 0 at a point. So if 0 is 0 at a point, then vorticity is 0 along the curves. And then we showed that if we can assume that this contraction is non-negative for everywhere, for the tangent vector V, then we found that within an affine this, and so if this is true and the initial value of the expansion is negative, we saw that by integrating the Reichel-Durius equation, we set a bound and realized that theta has to go to -infinity at a finite affine distance. So this is, and we know that we define the conjugate points by being the ones for which there is a non-vanishing Jacobi field that is zero at the pair of points. So if there is a non-zero Jacobi field, it's zero P in Q, so they are conjugate to each other. So this this theorem, this focusing theorem, sometimes called, they give you a criterion for identifying when there are conjugate points in a congruence. Then we discuss the energy conditions and why this should be reasonable. Then I comment about these certain properties that you obtain by taking variations of the arc length in the first and second order. And we establish as well that if a point can be reached by a causal curve, that it's not a time-like curve, so it can be reached by a null geodesic. All right, so with that, we are in position to start today's discussion. So the first part of the discussion is to establish that the event horizon is a achronal set. Right? So that is to say that the I plus of H intercept doesn't intercept H itself. Curly H is the horizon, the entire horizon, the boundary of B. So for that, we first show that I have a diagram here which is superior in the blackboard, that is superior to the diagram that I had in my notes. The light isn't the best, okay. Yeah, the light is in the back. I'll show you better. So the idea is, so if there is a point, so you suppose Q is in the horizon, then if there is a point P in the path, so pick a point in the path, the causal path of Q. Well, let me just algorithm. So you pick a point in the chronological path of Q. So there must be a neighborhood, because we saw, as a consequence of those last theorems that we were discussing on Monday, we saw that the chronological past and futures are open sets. If they're open sets, then there is a neighborhood. So Q is in the chronological future of P, but because this is open, the I plus of P is open, so then there is a neighborhood of Q that is contained in I plus of P. But then, because this is the boundary, so it intercepts. So this neighborhood of V of P must intercept the exterior of the black hole. I have this inclusion that I wrote here, right? I have this inclusion that I wrote here, which shows that P must be in the exterior of the black hole. So conversely, so this is clearly a time asymmetrical, because conversely, if P is, so this shows that I minus of a point in the horizon is in the exterior. Conversely, I plus of a point in the horizon is in the interior. So this is time asymmetrical, as the definition of the black hole is time asymmetrical. So there's no surprise here. And the diagram showing the reciprocal is just underneath it, right? So it's the same idea. If Q is in a point in H, so then P in the chronological future of it, then you know that you use the openness of I plus, find a neighborhood, and perform the same inclusions. Now, to show that it is achronal, then you pick a point in the horizon that I denote by R, then you suppose that R is in the chronological past of Q. Now, again, you'll use that I minus of Q is open. So there is a neighborhood so there is that's what I had written here. So there's a neighborhood contained in the chronological past of Q that is contained in the past of the horizon. But R is with R in that neighborhood. But I minus of H is open, and by definition, it cannot intercept its boundary. And that's a statement that, yeah, that's, because every point in a boundary, in the topological boundary of a set, has to have a neighborhood that straddles the interior and the exterior of that set. So that contradiction proves that the horizon is achronal. Now you might feel that we are getting really close to the area theorem, because as I mentioned on Monday, if you have a congruence of geodesics, there are no geodesics, and they possess a pair of conjugate points, so then there is a time-like curve. So say in a conjugate point between P and Q to be concrete. And so then if they are conjugate, so you know that there is a time-like curve connecting P and Q. Well, but that's the same as saying that these curves, the no geodesics I started with, are not achronal. So in the horizon, because the horizon is achronal, there can be no pair of conjugate points. And we had that focusing theorem. So you see that everything is starting to tie out together to the area theorem. Okay, now the next is not super, it's not crucial, but I mentioned that we can endow H. So now, for now, H is just a set. But then we can, but then it's possible to show that then H is in fact a submanifold. It's not only immersed, but it's also embedded. So the idea to show that you can endow H with the manifold structure in itself, that inherits from the manifold structure of spacetime, is to pick a point in the black hole and start and introduce Riemann normal coordinates around that point, and realize that oh, I don't have a diagram. Oh, but I have it here. Okay, that's fine. And you realize that the lines of constant. So you imagine that x0 is time-like. So the points, so the curves that have all the spatial coordinates constant, they must go to the past and the chronological past and chronological future of Q, and they must also intercept the horizon exactly once, because the horizon is achronal. Then you can look at the value of x0 at the intersection, and well, and then I write this inequality here just to show that, because this reveals that phi has some level of continuity. It's a Lipschitz continuous function with constant 1, because this is 1, there's 1 multiplied here. So this is just to show that this is not crucial, but this to show that phi is not just an immersion, but it's also an embedding. So you have this continuity, but that's not as crucial. The point is that you take the value of the intersection, and you imagine there is a map coming from the neighborhood in which I can define this coordinates intercepting to the black hole to R3. So that is the manifold structure that you can introduce on H. This is, of course, is just a local chart. You need to repeat it for various points to obtain a full atlas. Okay, now. Okay, so let's keep in mind what is missing. So we know that the horizon is achronal. There are no conjugate points. If there are no conjugate points, then and you have that focusing theorem. So yeah, all the geodesics can be on the generated horizon can be extended indefinitely. So it's enough to show that the value of the expansion at any given point cannot be negative, because if it is negative, I take that as an initial point, and I find a pair of conjugate points on the horizon. So we have to show that we can extend the geodesics of the horizon indefinitely. Well, and they are geodesics. So let's sketch this proof. Actually, it's quite intuitive, so that's why I'm not going to bother showing the details of the construction, but I'll show how you do it. I will comment on how you do it. So we have to show that every point on H lies on a future inextendable, no geodesic, with no future endpoints. So, well, I mean, you can imagine that, because let's use the definition of what the horizon is. So imagine there is a sequence of points in the exterior, so in the exterior of the black hole, that converges to a point on the horizon. So that's why I denote by P sub n. P sub n is a sequence of points in the exterior that converges to a point in the horizon, on the horizon. But because each Pn is in the exterior, by definition, I can connect this point to square plus, to the future no infinity. So that each of these curves I denote by lambda sub n, and each of these curves is, by definition, future inextendable. So let's see what's happening. You have a family of curves, so you have a family of points that's converging to a point in the horizon. In each of this, through each of these points of the sequence, it's connected to a future inextendable curve, to square plus. What happens here? Right? So you can imagine I can build a curve out of these points, and you do that by constructing a limit curve. The idea here is you start picking subsequences. So at every point you consider balls centered on point P, that is spheres, unit spheres in Riemann normal coordinates, and you look. So because that is closed, so you look at the intersections of the points of the family of the curves with the points on this surface, and you define a point that's going to be part of the curve that we are building as the limiting curve, as in the limiting point of the curves. Okay, so the ball itself is closed, so it contains all its accumulation points. So you take the limit of the intersection of each subsequent curve. Unfortunately, my drawing is a little bit not clear here, but imagine there's this interception happening at the boundary. So you define the point as the accumulation point of these tiny intersections. Now what you have to do is you have to repeat this procedure by changing the radius of this ball. So you have to change the radius of this ball for all possible fractions, so all possible rational numbers between P and whatever this radius is. And then you get that, so you get this bunch of points that I want to declare to be part of my limiting curve. Then I take a closure of that, because this is going to be dense in the real numbers, and well, the mapping of those real numbers. So then you have a segment of the curve. Then you move the point P to other points, and you can continue defining this limiting curve indefinitely to the future. So that's how you construct a limiting curve. Then that's going to be the horizon. If there were a point in lambda in the exterior, then lambda itself would connect P to the exterior. But that's impossible, because P is closed. So if I could connect that, so then this point would also be would not be part of the boundary that's set. So that shows that the curve that we just constructed is entirely contained in the event horizon, and you can continue it indefinitely to the future. All right. So what can go wrong now? So now I know it's inextendable. So all I need to do is to show that at the point, well, two things could go wrong. First, I have to show that the value of theta is positive at any given point, because otherwise it would provoke focusing, and I know that the focusing would have to happen at the horizon, because the horizon is inextendable. So whatever the finite value that produces the focusing theorem gives us would be reached, because every curve in the horizon is inextendable. So that would imply that the horizon cannot be achronal, because there are a pair of conjugate points. So there is just one way out, which is what happens if if the generators hit singularities. And that we have to exclude by hand. So let's introduce an assumption that excludes the possibility of having this curves fitting singularities on the horizon, and that's the assumption that I write here, that the space-time is future asymptotically predictable from sigma, and sigma here is to be thought of as a partial Cauchy surface. Partial because we don't need to assume that the entire space-time is globally hyperbolic, but we need to assume that the exterior is. So if you're given any set, so and any partial, any surface sigma that's achronal and edgeless, then the future and the entire Cauchy development of that can be thought of as space-time on its own that is globally hyperbolic. But so that's why I'm saying that it's partial Cauchy surface. Nothing about the interior needs to be stated here, only the exterior. So the assumption, the name of this assumption is black holes that are predictable, asymptotically predictable, future asymptotically predictable. So that assumption is that the future no infinity is contained within the future Cauchy development of sigma in the conformal with the boundary, the manifold with the boundary. So that's this M, perhaps a little bit confusingly, but this this M bar, which topology, this is well, now these two boundaries play a role. So this boundary that I denote by this partial derivative symbol is the manifold boundary, and the point, the dot over the latter denotes the topological boundary. Okay. So yeah, so why that? Why that? Because I plus is part of the boundary. If you remember from, well, what feels like forever ago, the first lecture last week. So put in simple language, more elementary language, this hypothesis excluding the possibility of naked singularities in the future of sigma. So that's a way of ensuring that my geodesics are not dying out at any point of the manifold. Right? Okay. So what happens? So let's show. So what remains to show? So let's prove the area theorem finally, right? So suppose we're going to find a contradiction if we suppose that at a point P, well, there are three possibilities at a point P in the horizon. So P, imagine that P is a point in the horizon. So the expansion of the congress of geodesics on that point can be either positive, zero, or negative. If it is positive, we're fine. If it's zero, we're fine. If it's negative, we're going to show that it's going to lead to a problem by what I've been repeating forever now. So if it's negative, so I can deform. It's a strictly negative. I can deform the surface. So imagine that P is a point. So imagine there is this partial Cauchy surface sigma here. And curly H again is the event horizon. So P is the point in the interception of the surfaces. So because the expansion is strictly negative by hypothesis at P, so I can deform the horizon H. I stay in sigma, but I deform the horizon just ever so slightly to the outside, so that theta continues to be zero. Continues to be negative at a point R, and that always exists because it's strictly negative. So now what happens? So then I define so the region in between these two surfaces, the region between H and intercepted. Well, that's what Dominic called straight H, and this deformed straight H, so to speak, defines a compact set. So what happens with the generate? So now let's take the causal future of this compact set and take its boundary. Well, and then I can apply my focusing theorem, because I'm assuming the null energy condition to hold, and theta is negative here, so there must be a conjugate point from R to the point Q where this intercepts, because, well, again, remember, this point is in the exterior, so it has to have a curve connecting it to square plus. And there must be a conjugate point in that surface, on that surface. But that's a contradiction. Because if there is a point, there is a conjugate point there, then this curve is not achronal, then there is a time-like curve connecting these 2 points, and these 2 points, so that this cannot be in the boundary, because it has to be in the interior, so that's the contradiction. So this shows that it was incorrect to assume that theta is negative at a point in the horizon. So the conclusion is that theta has to be non-negative everywhere on H. And in further assuming that the space-time obeys the null energy condition everywhere, and it's asymptotically future predictable from a partial Cauchy surface sigma, what we have? Okay, we have, so like to measure there, we have not one Cauchy surface, but 2. One sigma 2 is in the future of sigma 1. So every node generator of sigma 1 has to cross sigma 2, because the generators stay in the horizon. There might be new generators coming in, but existing generators can never leave. So any generator that crosses the first interception, straight H1, has to cross straight H2. And we saw that the area of cross section of this congruence is the rate of change is non-negative. So then the only conclusion is that the area of straight H2 is at least the same as the area of straight H1, and that's the area theorem. I give here credit to Stephen Hawking in 1971, but I must say that Hawking did not use his hypothesis of future predictability. Instead, he assumed that every generator in the horizon is future and extendable. So he had a weaker. That's the first formulation. 1971 is the first formulation of the area theorem. Since then, we managed to have this version I'm presenting to you, which is a little bit more, the hypotheses that you need to prove it are a little bit more under control. You know exactly what's going on and what needs to go wrong for this conclusion not to hold. Okay, so now this is also known as the second law of black hole mechanics, because it closely resembles the second law of thermodynamics, because we know there's this association, this analogy between the area, a constant times the area, and the entropy of the black hole that was coming from the first law of black hole mechanics. So this is a nice and analogous result to the second, at least to certain formulations of the second law of thermodynamics. Okay. At this point, I don't have notes anymore because there's a lot more to cover, and I'm just gonna discuss this face to face with perhaps with the aid of the blackboard behind me. We are settled. We have the zeroth first and second law of black hole mechanics, and an analogy between that and the laws of thermodynamics. Okay, so let's. Okay, first of all, there is an analog of the third law, which I'm going to talk about it in a second. But before we go to that, it's very important to take a step back and look at what was needed for each of these three results that we got. So we saw the formulation that I presented on last Wednesday for the zeroth law. It was clear, and I mentioned that there are results coming from quantum field theory in curved spacetimes that allow us, and the certain conditions which are a little bit more restricted. Well, they are more restricted than just having a bifurcating horizon, but it's well understood that there is a thermal state living in that space-time with a temperature that coincides with something proportional to kappa, which is constant throughout the horizon. And that proportionality constant was 1/2 pi. So it makes sense. That's how we understand thermal equilibrium. You leave a pair of systems to reach equilibrium, and then we assign temperature. If they are in equilibrium, then you assign the same value of the temperature for the two systems, or two parts of the system. So it makes sense to assign a temperature to the bifurcate killing horizon that is kappa around 2 pi. And if you combine that with the first law of black hole mechanics, the term that plays a role of TDS was kappa 1/8 pi kappa times the variation in the area. So there is a very natural splitting here that we didn't have before. Before Hawking radiation, we wouldn't have. There would be no way of trying to find out what the proportionality constant would be. And in fact, 1973 as well, the same year BCH paper, there was a paper by Bekenstein in Physical Review D, in which he was trying to push the idea that black holes would have to have entropy, because otherwise you wouldn't be able to violate the second law on the exterior. And in that paper, he tries to find the proportionality constant and he gets it wrong. But of course, because if you want to endorse the analogy with anything physical, then you have to say what the values of these constants are. But if you're just taking the viewpoint that these are just an analogy, then you're fine. It's just there is no need to find this proportionality constant. And it must be said that you could take the view before the discovery of Hawking radiation that it was no more than an analogy. For example, you could get the view the following. Well, we know that. So imagine a thought experiment in which we put a black hole and let it trade energy with a surrounding medium that is in thermal equilibrium. So the medium means in thermal equilibrium. Then you stick a black hole in there. What happens? Well, if the black hole has any positive temperature, this can be, because then it could find a medium at even lower temperature, and the black hole would have to emit more energy than it absorbs. But that's not possible. So the temperature of a black hole would have to be exactly zero. So that's the rationale for the classical theory. Now we know better. As we mentioned a couple of times. So if black holes radiate, so that this argument fails. And it doesn't fail because that's an interesting point. It doesn't fail because anything is escaping from the black hole, because one thing that was clear from day one of this mini course is that by definition, nothing can escape from a black hole. What went wrong there is the assumption that whatever energy the black hole has to absorb has to be positive. That's what's wrong. That is to say, what we are violating here are the energy conditions. And that's what the conditions in which Hawking radiation violate. And that's why the argument fails, that the temperature is zero. Okay, with all that, then we are safe to assign a temperature to the black hole that then leaves a quarter of the area of the event horizon to play the role, in general relativity, to play the role of the entropy. But it's dramatically different. The nature of derivation of the first and zeroth law are dramatically different. The first law is purely kinematical, right? I sketched how you could use an elementary derivation of a KMS state in such space-times last week, and you saw that Einstein's equations weren't used anywhere. It's just a kinematic property. But for the first law, yes, I need to say something about how gravity behaves. In that case, for the first law of black hole mechanics, as was presented by Dominic, he made use of Einstein's equations. So if you want to promote the first law of black hole mechanics to the first law of black hole thermodynamics, it's not enough to do quantum field theory in curved spacetimes. We need to include the back reaction somehow, and that can be done. So, and that can then the two versions. So I mentioned there was, I mentioned on last time we met on Monday that there is a local, so to speak, a local version of the first law of black hole mechanics, and there is a generalization of the first law of black hole mechanics as Bardeen, Carter, and Hawking showed in a global version for diffeor preserving theories of gravity. And it's important to be a bit more open of what we call Einstein's equations in semi-classical context, because it needs renormalization. So because the energy momentum tensor, TAB, if you don't renormalize, that object is divergent even in Minkowski vacuum. So that can't gravitate as it is. So there has to be something else. So some level of renormalization imperative to make sense of what gravity can be. So that's a semi-classical approach. Let's couple the geometry to expectation values, normalize. But because of normalization, then you need to add counter terms. So you can always imagine that you're writing all the counter terms that you might have on the left hand side of Einstein's equation. Then you no longer have Einstein's equations per se. So that's important why you want to be a little bit more flexible to saying that. But if you assume a version of semi-classical equations, so it's been worked out, and you can have the first law of black hole thermodynamics now, or now we call it damn thermodynamics, with a semi-classical coupling, both the local and the global version. So that makes one safe with identification in GR. Let's talk in GR, because if it's not GR, the expression for the entropy is a little bit different, but not in an important way. So in GR, we are safe to assign for stationary black holes a quarter of the area as its entropy, because that's the thing that obeys the laws of thermodynamics. Now, there's a cautionary tale here. We know that this identification holds for stationary black holes. An analog of this of the second law has to be dynamical, and it might. Okay, first of all, a naive analog of black hole of the second law of black hole thermodynamics, which would be saying that the entropy of the black hole has got to increase or not decrease, runs into trouble because you have Hawking radiation and conservation of our energy arguments. Dominic is going to talk a little more about the process of evaporation on Friday. But for now, let's just think that by conservation of our energy arguments, if the black hole is absorbing a bunch of negative energy, so at infinity there's going to be energy, there's going to be a positive flux of energy in infinity. So conservation of energy arguments, we imagine that the black hole has to lose mass. So if it's a Schwarzschild black hole, it is something that it has nothing else to lose, it's got to be losing area as well. So there's got to be a violation of the area law in a very well-controlled way, because it's, again, there is no reason. Well, we know that then the null energy condition is, we know it's a bit too strong because this is based on curve on a fixed curve quantum field theory on a fixed background, but it's very reasonable to expect that the null energy condition is violated. So there is no contradiction with the theorem, but it does say that the area is expected to decrease. So whatever the second law of black hole thermodynamics is going to be, it's going to be modified, and that is, and that is the generalized second law of black hole or thermodynamics. Now, the statement is that if you sum the entropy of the black hole with the entropy of the exterior of the black hole, it's only the sum that's supposed not to decrease as one goes to the future. Each individual term can decrease. So in a highly classical regime, the entropy of the exterior might be decreasing as you inject matter into the black hole, and the area of the black hole keeps increasing. So that's a way of preserving the generalized second law. A second way of preserving the generalized second law is by emission of Hawking radiation. Now the area decreases, but the emission of radiation compensates for that decrease in that it increases the entropy in the exterior. So that's a way of obeying the generalized second law of thermodynamics. And for a time, people started to think that was reasonable. Bekenstein would be delighted with how this generalized, because that's the intuition he had even before the discovery of Hawking radiation. And it kept surviving to certain thought experiments. I think there is one that is particularly interesting because we know on general grounds, well, nowadays we know on general grounds that nothing could go wrong, but at the time, people were so certain about it. That was proposed by Bob Garrow. So imagine what happens if you have a highly entropic box at infinity, and you slowly lower to the black hole, and once it reaches the horizon, remember the redshift there is 0. So the energy, the local energy injected into the black hole is 0 if you release the content of the black hole, the box into the black hole. So you would be transferring 0 energy to the black hole, but a lot of entropy because you're not because you're disappearing. So all the entropic matter that was in the exterior now disappeared because you injected into the black hole. So that would lead to an apparent violation of the generalized second law, because you're disappearing the energy from the entropy from the exterior. You inject no energy. So if you write a first law of black hole mechanics, that there is no change in area, so there is no change in the entropy of the black hole, and then you disappeared with the energy, with the entropy in the exterior. Remarkably, because this is a quantum process, I mean, you trust this thermodynamics because of a quantum process. So let's take quantum seriously. So if there is this. So because there is the equilibrium condition obey Tolman's relation, as I showed the Tolman relation, that equilibrium condition in a presence of gravitational field does not mean the entropy is uniform, the temperature is uniform. It has to change from place to place according to the redshift factor. And because the exterior is a radiation, and radiation is extensive, then you can apply Gibbs-Duhem relations to the exterior, to this matter in the exterior. So the gradient in temperature generates a gradient in pressure. And the gradient in pressure exerts a force into the box. So to lower the box to the black hole, you have to inject work. And that's how, and then Unruh and Ward performed the calculation and showed that taking that into account, it prevents you from violating the generalized second law. So at this point you start to take the generalized second law very seriously. And in fact, nowadays we understand it much better. For example, if you insist in the identification of the area with the entropy, even for dynamical black holes, again, one has to be careful with the identification, because the identification is made for stationary spacetimes. Of course, area classically is a monotonic function, and the entropy is believed to be a monotonic function, but the identification of the qualities is grounded on the first law of black hole mechanics, and that is, or thermodynamics, if you want to incorporate this, you allow for quantum matter to be traded. So that identification is for stationary black holes. So yeah. But if you continue to believe that, and you interpret the second law as a localized process in the sense that the area that they're identifying with the entropy is not the area of straight H, but well, it's the local areas of the expansion. It's the theta integrated. So that proof was completed by Aaron Wall in 2011, if I'm not mistaken. But if you want to have something more global, and you don't want to commit with that, then there's an argument I made in 2020. So let's artificially make the black hole evolve from a stationary space-time to another stationary space-time. By that I mean, there is a region in which it's isometric in the past to stationary space-time, and a certain Cauchy surface of the future of which the space-time is isometric to another different stationary space-time. This is artificial because black holes, if you let black holes be, thermodynamical equilibrium are not stable. And there are many ways of convincing oneself. My favorite, Dominic's going to talk a little bit more about this on Friday, so let me not spend too long saying that. But an artificial way of ensuring that you can move from a stationary situation to another stationary situation, or an equilibrium situation to another equilibrium situation, is to confine the black holes in a box. So if you do that, then you say, well, I don't know what the dynamical entropy of the black hole is, but I know that in this and the past of this it's the stationary, so I know what that is. In the future, it's stationary, so I know what that is. And then you can also prove a version you can also prove the generalized second law for any entropy that coincides with this entropy. But that is assuming that it's an event. There is an event horizon. It's a global version as well. Outside of equilibrium, well, it's still somewhat of an open question. Okay, I'm looking here because even though I don't have lecture notes, I have some bullet points, so don't forget to mention. Okay, on to the third law. Let me say something about the third law, which I completely neglected so far. The third law is, well, again, what we mean by third law of ordinary thermodynamics, different authors call different things the third law of, even the second law for that matter, but the third law is even less consensual. So anything like the Nernst theorem, anything that says that if you go to zero temperature, it's going to have zero entropy, that's hopeless in black hole physics, because you can take extreme solutions. For example, Nordstern black hole that has kappa equals 0, and it's still a black hole, so it still has an area on it. So that version, forget. But there are other versions, and I think the version that has closest analog to a version of black hole thermodynamics is a theorem proved by Werner Israel in 1986. So that theorem says that if you start from a positive kappa in the past, and you assume the weak energy condition for the matter, and the energy momentum tensor is bounded from above, so it doesn't blow up at any point, then at no finite time, you can reach kappa equals 0. So that is similar to saying that if you start with the system at a positive temperature, it's infinitely hard to let its temperature to become 0. So that is there is this analog in black hole physics as well. But the reason why I am not emphasizing that result too much is that this is okay. First, what is the status of the third law and what it really says, and there are many ways in which it's not analogous to thermodynamics. So I personally don't think that it's as important as the results for the thermodynamics of black holes. I don't think it's as important as the other results. And there are many results that can be proved. They're not this one, but ever since Penrose had his first singularity theorem in 1966, and it continues even up to the present day. I mean, this community is small, but there are people working on certain issues in mathematical relativity today, but to the present day. But ever since there are many theorems that were proven, and they can be proven using the same type of methods that have been developing in this mini course. And they are all very interesting. And I don't think this theorem by Israel is more interesting than others. So let me give you an example. An example that can be proven using very similar techniques to these that I showed. So this type of so using this type of techniques, very similar to this, you can show something very interesting, which is the apparent horizon. Okay, well, maybe that's a good time to define what apparent horizon is, and that's also useful for singularity theorems. So give me a second, let me. So we had this characterization of black holes that is sometimes called teleological, because you have to have the knowledge of the future to identify where the black hole is. But can I have an idea if I'm inside a black hole? I mean, do I have to be blissfully unaware that I'm inside a black hole all the times, or in more physically realistic situations, I can have a hunch whether or not in a black hole? And then Penrose came up with this idea to prove the singularity theorem. He came up with an idea of a closed trapped surface, and that is, so it's not entirely local, because demanding that the surface is trapped. Demanding that the surface is closed is not obviously it's not a local thing. Demanding that the surface is trapped, it is, because the idea is, if you start with a space-like to surface that's closed, and well, if it's in Minkowski space-time, then you can imagine the light cones at every point of that surface emanating from there, right? And then, well, you could say, well, the area of this inner envelope is naturally, even in Minkowski space-time, is naturally smaller than the area of this initial surface that I had. But the area of this outer envelope should expand in Minkowski. So that's what you normally expect. But sometimes the theta associated with both the ingoing and outgoing congruences are negative, in which case the surface is trapped. So that's type of construction. So if you assume a global condition plus the existence of a closed trapped surface and energy conditions, you can prove that geodesics can't be complete. Time-like, no geodesics can't be complete. There's more than one version of this theorem. There are plenty of them. So there is a notion of apparent horizon. There is the area, the region in which closed trapped surfaces live. So what we can show using very similar techniques that I presented is that this apparent horizons plus energy conditions and predictability lead to saying that they are inside a black hole defined in the way I did here for this mini course. So this is one example. Another example. Oh yeah, there is a question. Yeah, go ahead.
Excuse me. I want to know about the surface of the black hole that you mentioned. It's about inside the black hole or in near the event horizon. I want to know what does it mean, the surface of the black hole, that the light comes up near that. Would you please explain it?
Yeah. So you're talking about this characterization that I drew.
Yes, yes, on the blackboard. You
Yeah.
said about the surface of the blackboard. Which part of the blackboard? Inside the blackboard, in the event horizon. Can you explain?
So let me start. So let me start for the final question. In classical theory, in which that's a theory that you can assume energy conditions, this notion is inside the black hole, the way we defined, that we've been defining here. So this is in classical physics. Now, what they are? So they are two surfaces that are closed, and theta is negative for both. For this theta associated with this ingoing being negative is not surprising. But if it is the outgoing is also negative, then you imagine that at that point, if you go to the future and an infinitesimally later time, things, including light rays, would have to be closer. Will be inside it, right? You will move closer to the center of this closed surface. So this is a trapped surface. So this is trapped. The one inside it is trapped as well, and the one inside is trapped. One inside is trapped. So there are many trapped surfaces.
Excuse me. It means that when we go out of the black hole near to the out of the black hole, the surface is the expansion of the surface. Yes, and when we go to the inside of the black hole, we have a we will go to the, for example, to the event horizon, or no, you know, about the imagination of the
to get to the event horizon, you do the opposite. You go as far as you can while keeping the surfaces trapped, because every trapped surface in classical theory, with energy conditions being assumed, no energy condition is enough. With the null energy condition, you go everywhere. You go as far as you can. So the idea of the parent horizon, the parent horizon is you go as far as you can, where you still have this trapped surfaces, closed trapped surfaces living inside.
Thank you very much. Thank you.
Yeah, so one of the results is that, and other results that you can prove is that black holes can't bifurcate, and that's important because the area theorem, as it is, the classical area theorem, leads to physical predictions. For example, there is a maximum amount of energy that you can extract from black hole mergers, because the sum of the areas of the black holes have to be at least as large as the initial black holes. It has to be the opposite. The final black hole has to have an area that's at least as large as the sum of the areas of the pair of black holes that merge together. So that places a bound of how much energy can be emitted through gravitational waves. These are relevant consequences. You can also predict things like superradiance and other stuff using that. But I got lost. Why I'm saying this? I'm sorry. I don't know why I start saying this. I'm so sorry. I don't know why I start saying that. But anyway, so you have these other results, which are also powerful physical results, and the no bifurcation of black holes are another example. So for that reason, I like to think of the third law as Israel's third law as in the same category of results that using these sort of techniques. But it exists. But when you go beyond classical physics, the third law is even more interesting as a conjecture, because it says that something quantum mechanically you can't create, also quantum mechanically, you can't create a naked singularity. And just like this thought experiment that I described using this box you can concoct other theorems like this, other thought experiments like this, and see whether or not they survive, and they seem to survive reasonably. So black holes seem to be indestructible in the sense that, I mean, even in a, so the area theorem says that, well, the area theorem clearly says that the black hole cannot be destructed by classical processes because the area can't decrease. Hawking radiation, if you look at even in Hawking's original papers in Communication and Mathematical Physics in 1975, if you look at that paper, it's there that the emission of Hawking radiation favors the ones that are thermodynamically favorable. So it emits more highly with high angular momentum. They favor the emission of high angular momentum more so than it loses in masses. So you can't overspin your black hole or overcharge it, as so to say. So there's something interesting there that's, as far as I know, is not understood from quantum field theory in curved spacetimes or from some classical gravity just yet. But they seem to pass some Gedanken experiments, in the same way. Let's say that the generalized second law used to pass in the past. Okay, one final remark is I mean, most of this is going to be discussed on Friday, so I'm not going to extend too much. But in semi-classical, so if you look at these proofs, the generalized second law, or you might or the first law of black hole mechanics as well, thermodynamics in semi-classical theory, you might be worried that these entropies are infinite because the entropies that appear in these derivations have to do with the von Neumann entropy of quantum fields, and they are known to be infinite once you trace out parts of chunks of a Cauchy surface. And if you're worried, you have all the reason to be, but there are two things that I would say to you. The first is these laws only care about variations of entropy. So even though the entropies themselves might be infinite, their variations might be finite. Actually, the first law proves that the variations that enter the first law are finite, that the Oxford proof. And there are recent works in renormalization group that suggest that once you turn on gravity, the entropies that appear, generalized entropies, the one that has the area, and the one that has this tracing out, might become finite again once you turn on gravity. So that would be a feature of the background responding to quantum matter, not just a property of quantum field theory in a fixed background. That we know that's not well defined. Okay, that's what I had prepared for today. For Friday, it's going to be a fun lecture, as I promised. Since I promised that it was going to be fun even in my first lecture, but that's because it's going to be a lot about physical aspects of operations and more details about what type of thermodynamical objects black holes are. But that's what I had for today. But if you have questions, especially questions regarding the black hole mechanics, that's the best time to ask that. So go ahead.
Thank you for the talk. I have a question about differentiability. So in classical
about what? Sorry.
Differentiability.
Yeah.
So we assume the classical space-time is a differentiable manifold, right?
Yes.
And then we define the black hole and its horizon. And can you tell me what can we say about the differentiability of the horizon?
Yeah, well, okay. So that's what we had. It's a manifold. It's a differentiable manifold on its own, and you can find a map that I had here. So that's why I had. Well, I didn't spend as much time talking about this, but this statement here is precisely concerning what type of differentiability you can have. So as a submanifold, it's an embedded submanifold. So that means, that is to say that the phi, the mapping, then that are defined in this way, is a homeomorphism in the induced topology on the horizon. So it is pretty smooth.
I think so. You mean it's a diffeomorphism?
Yeah,
I mean,
yeah. It's a there is a well, I'm saying that there is a homeomorphism. I mean, there is an embedding, so it's an immersed manifold, and it's homomorphic in the induced topology on the horizon. So it's
okay. So yeah, because I was thinking, like, from the definition of the black hole is like whatever is outside of the past of the future, right? So like from that, it just looks a bit topological, like that kind of definition.
that's right. Yeah, that's entirely
It's
right.
not obvious.
Yeah, I love that you said that. That's precisely right. That's true. That's true. And that's why we had to work a little bit harder. I mean, if you assume that, as Hawking did, if you assume that everything is very geometric, it's a lot easier to prove the area theorem. But that's why we had to endow. Yeah, it turns out that there are nice geometrical properties of the event horizon, but by definition it's a topological definition as well put. Yeah, I agree.
Okay, thank you.
Yeah, that's a very nice remark. Thank you. It shows that you're following.
Bruno, should I link your presentation on IFT about black hole thermodynamics?
Unfortunately, half of it it wasn't recorded, so I don't think it's useful.
Oh, okay.
Right, because if you're just gonna listen to me speak in the second half of the talk, then I think it's not as useful. But yeah, I mean, you may leave it, but I don't recommend it, because someone messed up the recording, and now it's not exactly. I don't think it's a useful presentation anymore. But feel free to.
Yeah. I don't know.
Yeah.
So I have one more question. Like, is third law, what third law you said, is that same as cosmic censorship hypothesis? Like negative singularity doesn't exist. You said that as per third law of thermodynamics, black hole thermodynamics. Is it not same as cosmic censorship?
Well, it's closely related. It's closely related, and you can see it's closely related if you look, for example, take the Kerr-Neumann solution and look, or just Kerr solution, because Kerr solution is advantage. There is advantage because Dominic wrote the formula for the surface gravity for kappa explicitly for Kerr solution. So if you look what happens when you get to the extremum case, you see that kappa goes to 0. And the extremum case is the case where you don't have an event horizon anymore, but you still have a singularity. You still have Kerr singularity without horizon. So saying that your kappa is going to remain positive, if you assume that, and at least in the Kerr family, it's assuming that you can't inject lots and lots of angular momentum in a black hole without injecting sufficient energy so that kappa goes to 0, and you destroy a black hole, and you're left with a naked singularity. So in that sense, it's related to cosmic censorship. There's more than one version. There's more than one version or a precise statement of what a cosmic censorship is, but that's one of them. Yeah. In equivalence.
One more thing, like does the proof of existence of a trapped surface depend on some energy condition? I missed that.
No. Well, what depends on energy condition is the inclusion, saying that what depends on the null energy condition depends on assumes Okay, what assumes the null energy condition is that trapped surfaces are inside black holes. That for that statement you need the null energy condition and the predictable black holes. The existence of trapped surfaces are an hypothesis. Even in the singularity theorem, it says that if you have trapped surfaces and other hypotheses, then you have a singularity. That's the content of the singularity theorem. So they are an assumption. That's a way of assuming. Well, that's a way of assuming that something like a black hole exists. So that's what I found a little bit unfortunate. If you look at the quote Nobel Prize 2020's Nobel Prize quotation, it says that Penrose had shown that black holes are a robust prediction of general relativity. No. He assumed black holes. So he showed that singularities are a robust prediction of GR. Right? So that's an imprecision of the Nobel Committee there.
Okay, thanks.
Excuse me, I have a final question about the entropy in general definition. In a general form, the entropy in any part of the black hole is equal. For example, when we believe that the entropy will increase, for example, in a singularity, inside the event horizon, outside the event horizon, on the surface of the black hole, the entropy is any part of the black hole will increase or no? Well,
look, okay. So that's an important question. I think the way I'm trying to build up things, I think I was trying to show that the entropy is not something you can localize. I don't know where the entropy is. Right? I assign the entropy of the black hole as a whole. So you say, well, what's the ion content? What's the entropy density? Look, I mean, we didn't have time to cover this. I mean, if instead of 6 lectures, this mini course had, maybe 9, maybe we would have time to cover some of this. But especially if you're looking at the entropy of black holes, for example, that appears in the von Neumann entropy, it is clear that it's not something you can localize. Sometimes in gases, for example, then you can define entropy densities, but not here. Not here. It's not anywhere in particular. It's similar to the definition of the Kolmar. Well, I mean, in a way, it's not. But there is some similarities in this globally defined quantity. So the entropy should be thought of as something globally defined in a similar way to the Kolmar mass. As you remember from last Friday, you may assign a mass over space-time, but not the mass density. Something that if you integrate over the volume, it gives you the value of the mass of the Kolmar mass, of the mass of the space-time, or the alien mass, for example. That generally doesn't exist in general relativity. Entropy even less so. So it's best to think of a. We only assign entropy to black holes because we have the laws of Black Hole Thermodynamics, and they can be assigned as you put them in equilibrium or something else. So that's a globally defined quantity that black holes ought to have, but that's not trying to localize it. That's my takeaway.
Because I asked it about, just about the information inside the black hole. I asked about the entropy for a most important question behind my brain about the information. I imagine that if the entropy, that we don't know, if it's in any part of the black hole is not equal, or it could increase, decrease, or is constant, we don't know. What happened to the information?
Again, information is also the property. So let's remove the black hole to convey this. Let's not think of a black hole. Let's think of Minkowski spacetime. And let's take the vacuum in Minkowski spacetime of a quantum field, for example. Now let's imagine I have an arbitrary division into the Minkowski spacetimes into two half Minkowskis, right? And defining a boundary by a three surface and say, well, everything to the left and everything to the right of that boundary. The original entropy is 0 because it's a pure state. It's a vacuum as a pure state of Minkowski spacetime. But at the moment I put the boundary there and I partition into two parts and say, well, it's the entropy of the half of Minkowski spacetime that goes from 0 to infinity. Where is the information? Well, how do I localize it? You know, it's some way you can say, well, it's there. It's in the other half you're disregarding, but how exactly is not exactly an easy question to pose precisely. Well, we know that it has to do. It's infinite because it has to do with UV correlations, and somehow you think, well, they might be not far away, but most of the information is encoded just close to the boundary that I set. Yeah, and there are good reasons to think that's true, but you know, I'm trying to encourage you to think of it in a not localized manner, in the same way as in Minkowski spacetime.
Thank you very much. Thank you.
You're welcome. Are there any more questions? Okay, so if not, I'll say goodbye for today, and I'll see you again on Friday for our last lecture, and I'll be around. We can discuss a little bit more in the end of it if more questions come about. For now, I say thank you, and I see you then.
Will you be co-hosting
Will
you be co-hosting the lecture on Friday or just your peer? I don't remember his name, sorry.
Dominic will be teaching. Well, we'll be present around. So in the end, we can have a final round of discussions and questions.
Okay.
We'll be around. Yeah.
Okay. Thank you.
Right.
Bruno.
Well, see you all.
Bye.
Thank you. Bye.